Okay, so when we see here in the given, this symbol here, that means parallelogram, right? So we're telling us EFG is a parallelogram. So that's our given. Yep. So number one, EFG H is a parallelogram. Okay, so parallelogram, that word is a vocabulary word, isn't it? Okay. So when I go to parallelogram in the back of the book, it's going to tell me what? The opposite sides are parallel. Okay. So based off of that definition, I should be able to say EF is parallel to HG, and EH is parallel to FG. Okay. Now, what we're trying to do here, maybe we should have mentioned this at the onset, is that we're trying to prove opposite sides congruent, right? If we look at that, it says, given a parallelogram, prove that EF is congruent to HG. Well, EF and HG, if we look at them in the picture, they are defined as opposite sides of the quadrilateral. So we're trying to prove that opposite sides are congruent. Same thing for the FG and EH then, okay? This is one of the, I guess this proof here is actually kind of fundamental in regards to all the other theorems that we talked about yesterday, or most of the theorems we talked about yesterday, okay? So there's about 6 or 7 steps here that are going to be consistent for this proof and the other theorems from yesterday. The next step that we have to do here is not all that obvious, okay? But whenever we deal with parallel lines, think back to chapter 3, okay? We always talk about parallel lines, and there's always a third line involved that we call it a what? Transversal. So we're interested in a transversal for these parallel lines. Now, there are already a lot of transversals up there. For instance, EH would be a transversal for the top and bottom parallel lines, right? Yep. And you can keep doing that all the way around the picture, looking at different, each one of those 4 lines up there, 4 segments up there, is a transversal for 2 respective parallel lines. However, none of those give us any information that we need. Think about what we did in chapter 4. In chapter 4, we tried to prove what congruent all the time? Triangles. Okay? Do I have any triangles up there right now? I could make one. What? I could make 2 sets of them, right? Give me a line that I could draw that's going to create 2 triangles. Okay? Careful. Sam? Okay.
I was looking at H and E.
Okay, so I could draw HF or I draw EG, right? Has everybody kind of visualized doing that in the triangles that we created? Yeah. And in regards to what we want to do, it does not matter which one you draw, but you've got to draw one of them. Okay? I'm going to draw HF, so I think it's probably a good idea that you guys do that as well. Okay? Why can I do that? But I can't do something because of what is going to happen next. I can only do something because of what is currently occurring. Should have wrote this down. That was definition of parallelogram, right? Why those lines are parallel, or segments are parallel. The reason I can draw HF, guys, back to, it's one of the first theorems, or I guess postulates that we talked about earlier on in the year. And it's something that you guys have known for a really, really long time prior to even this course starting. How many points do you need to create a line? 2. Is H a point? Is F a point? So we know, even though it wasn't drawn in there, that we could connect them with a straight edge and make a line there, right? Okay. So there's a lot of different things here that we can write. I'm going to write as my statement, I'm going to write construct or draw segment HF. And now my reason, I'm going to say 2 points determine a line. You guys remember talking about an auxiliary, I have trouble saying the word, auxiliary line? Okay, if you want to put that in there, that's fine. Is HF a diagonal?
Yeah.
Okay, someone will ask, I say, can I use definition of diagonal? Absolutely, because a diagonal is a segment. Therefore, that segment had to have 2 endpoints, H and F, right? Okay, so I would agree that there's a couple different things that you could write there. Okay, but that line does absolutely exist. Okay, so why do we want to do that? Well, when we do that, we create, and I'm just going to do this to make things easier for us in regards to recalling these angles. But I create angle 1, angle 2, angle 3, and angle 4 when we do that, right? Okay, let's look at one set of parallel lines. Let's look at the left and right parallel lines. What does that allow me to say now? If these two lines were parallel and this is my transversal, what can you tell me? Okay, so looking at these, I'm going to say 2 is congruent to angle 3. Angle 2 is congruent to angle 3. And I'm going to put in parentheses here that was because EH was parallel to FG. You don't have to do that. And a lot of times you're not asked to do it. Maybe on Math Excel, sometimes in the drop-down window, that'll be like in parentheses somewhere. The reason I'm doing that is because what's that read? Or what is the y of y angle 2 and angle 3 are congruent? Okay, so alternate interior angles theorem. Okay. Now the reason I put in parentheses here this statement is because I'm going to use this theorem again to talk about angles 1 and 4. Okay. But based off of the lines that I have highlighted right now or shown in my picture, 1 and 4 are not congruent because of those parallel lines right now. Does that make sense? Yeah. 1 and 4 are congruent because of E and F and G and H being parallel. Okay? So I'm going to, just for the sake of visualizing it, hide those two. And now do you see that because that one and that one are parallel, we create angle 1 and angle 4? So I'm going to say angle 1 is congruent to angle 4, and that's because E and F, or EF, was parallel to HG. I'll put all that under statement number 4 and reason number 4 because they're both alternate interior angles there, right? But I need you to understand that one congruency comes from one set of parallel lines in a transversal, and the other congruency comes from a different set of parallel lines in that transversal. Okay. All right. So looking then at this picture, what are we trying to do here if we have triangles in our picture? In chapter 4, we were always trying to do what with those triangles? Okay, so yeah, we're looking for a side, 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 a side, an angle, side, angle, or an angle, angle, side statement, right? Okay. Is side, side, side kind of a stupid option? Yeah. Is side, angle, side maybe a stupid option? Yeah. Okay, and those were bad options because I've got currently 2 sets of angles congruent on the left-hand side of my proof here, right? So I probably use one of the congruencies that has 2 angles in it. Okay. So now which one is going to be the best one here for us to use? Angle, side, angle. So I need a side, right? What side do I put in my proof? Which one? HF. So HF is congruent to HF, right? If we've got that segment in both triangles, we're going to use what property to say it's congruent to itself? Reflexive, good. Okay, so you're telling me that the order of parts then is ASA, right? So once I have those 3 congruencies, 1 congruency, 2 congruency, 3 congruencies, we can now say that these 2 triangles are what to one another? Congruent. So I'm going to say triangle make sure you name them right. I'm going to go EFH is congruent to triangle. Okay, so if I started at E, where have I got to start in the other one? G. I went to F, which had this one mark in it, right? So I go to H, and then finish at F. And again, that reason, nope. Two triangles congruent. This was the reason for that. So now you want to, because that's not what I want to prove, right? I want to go a little bit further. So now you got in the mind, I got to use a CP-CTC thing, right? Okay, well, look at what we're trying to prove. EF and HG. If I look at EF, first two letters there, HG, first two letters there, are they going to be congruent? Okay, so EF is congruent to GH or HG. Somebody in the last class wanted to argue whether these were the same. If I say EF is congruent to HG, is that the same thing as EF congruent to GH? Yeah, because so segments, you can read them forward and backwards, right? So that's true. Now, in the same exact statement, can I say FG, which would be that letter and that letter, right? Is that the same thing as EH, which would be the first letter there and the last letter there? So we can go ahead and say FG is also congruent to EH. And what's my reason? Good. CP-CTC. Okay. Corresponding parts, so matching parts of congruent triangles are themselves congruent as well. Okay, so that's great. That's awesome. That just said we start with the parallelogram. We can, using chapter 3 stuff with parallel lines, chapter 4 stuff with triangles, we can learn some properties of parallelograms, right? Yep. Now, one more question here. What do you know about angle E and angle G? Why? Right, so E is the first letter here, right? G is the first letter there, right? So I could say that E is congruent to G by CP-CTC. What kind of angles in regards to their position to one another are E and G? They're corresponding for the triangles. If I look, let's just get rid of the triangle. Let's look at the parallelogram. They are what for the parallelogram? Not consecutive, which what word would we look for there? We'll be looking at this one. Opposite. Okay. Non-consecutive in a parallelogram, non-consecutive would equate to opposite. It'd be the same. Okay, but we want to say opposite. So here's my question. When I want to prove the theorem that says opposite angles of a parallelogram are congruent, is it the exact same proof there, except for step 7 is now talking about angle E congruent to angle G instead? Okay, still going to be a reason CP-CTC. Now what that would do, if I was going to go that route, and we might do that tomorrow, we'll see. That would only give me that angle congruent to that angle, right? Yeah. Okay. In order to get the other set of opposite angles to be congruent, I would need to do the whole proof again using that diagonal. I'd go through and use essentially these 6 steps again with that diagonal, and then I could use CP-CTC to say that those two angles are congruent. Does that make sense? And a lot of times what you can do in a proof like that is, because you're going to do 6 steps, make a conclusion, and then go back through essentially do the same exact 6 steps. Obviously, you'll have different angles and stuff like that to talk about, but you can maybe write, I'm going to go through the same 6 steps, but with this diagonal, and you will see that the conclusion is that I get angle F and angle H to be congruent. So you really wouldn't have to go through all 6 steps at the same time. Does that make sense? You just kind of write out in words what your plan would have been. With that, hopefully you realize you see 2 sets of kind of proofs that we've done so far this year. We have done parallel line proofs, right? Okay, so steps 1 through 4. We have done triangle congruency proofs, right? And that's kind of steps 4 through 7. Okay, this is just merging those together. Okay, and I think we mentioned this yesterday. The nice thing about this course is chapters 1 through 3, we've knocked out everything that we need as kind of fundamental concepts to build the rest of the course. It's now just piecing those together accordingly. And now as we learn something new here in chapter 5, I guess it's chapter 6, maybe something later on we use from chapter 3 in chapter 6 to make something in chapter 9. Does that make sense? Okay. I don't have anything else for you today, and that's a good thing because the bell's going to ring here in a moment. But I sent you an email with a Word document in it, and there's essentially a coordinate plane proof for your homework tonight. Did you finish it? 100%?
Happy birthday.
Today's your birthday? Happy birthday.
You listen to Alex.